All right, today we're going to go deep. I mean, way down into the engine room of AI, past all the usual headlines. We're talking about the architectural innovations that actually make these massive models possible. And we're going to focus on a really brilliant one you've probably never even heard of: attention residuals. But first, I've got a question for you, a real puzzle. We all kind of assume that with AI, bigger and deeper is always better, right? So, why is it that when you keep stacking more and more layers onto a transformer, it can actually start to get, well, dumber? This weird counterintuitive problem is right at the heart of one of the biggest challenges in AI right now. And yeah, that right there is what we call the deep transformers dilemma. As we push these models to incredible sizes, to hundreds or even thousands of layers, we start running into these fundamental flaws in their original design. Flaws that can seriously mess up their ability to learn anything useful. So the main culprit here is a problem called information dilution. Imagine you whisper a secret at the beginning of a super long line of people. By the time that secret gets to the very end, it's just garbled nonsense, right? Well, that's exactly what happens inside a deep AI. The normal connections just keep adding the output of every layer on top of the last one. So that really crucial information from the first few layers, it just gets completely washed out in a sea of noise. And get this, information dilution? It's not even the only problem. We also get things like rank collapse, which is where the model starts to see different words as basically the same thing, losing all that important nuance. Or even worse, entropy collapse, where the model just gets stuck. It freezes, fixating on a few random words and just stops learning entirely. It's a whole mess of problems. So how in the world do you fix that? Well, the answer wasn't just to build a bigger information highway. It was to build a fundamentally smarter one. And that meant a major shift in how researchers thought about information flowing through a network. This right here was the big shift in thinking. Researchers realized the old way, just passively adding up outputs, was totally broken. The model itself needed to become an active participant in its own learning, intelligently routing information exactly where it was needed most. And that's what leads us to this amazing breakthrough from the team at Moonshot AI. Yep, the folks who made Kimi. They came up with a technique that tackles this active routing problem head-on. They called it attention residuals. So here's the absolute core difference. A standard connection, that's just passive accumulation. It just blindly adds the new layer's output to everything that came before. But attention residuals, or ATNRs, that's active retrieval. Each new layer intelligently asks the previous layers for the specific information it needs. It's like the difference between being in a room with everyone shouting at you at once versus being able to ask one specific person a direct question and get a clear answer. Okay, so if we're going to get a little more technical for a second, Adin Sontelvis takes that amazing attention mechanism, the tool that transformers use to figure out how words in a sentence relate to each other, and it turns it inward. It applies it to the model's own layers. So now each layer can literally pay attention to all the previous layers and pull out only the most relevant bits of info it needs to get the job done. Now, if you're thinking ahead, you've probably already spotted the catch. I mean, the attention mechanism is super powerful, but we all know it's also really computationally expensive. So applying that to every single layer in a gigantic model, doesn't that sound like a recipe for a total monster of a network that's just impossibly slow? And you'd be absolutely right. It would be. And that's exactly why the team came up with this really elegant and efficient solution to make it all practical. They called it Block at Res. Here's how it works. It's actually pretty simple in 3 steps. First, you group all the model's layers into just a handful of blocks. Second, for any communication that happens inside one of those blocks, you just use the old, super fast addition method. But then, and this is the clever part, for communication between the different blocks, that's when you use the powerful new attention mechanism. So you really get the best of both worlds. You get the speed where it doesn't matter as much, and the precision where it really counts. Okay, so the theory is really elegant, but does it actually work in the real world? Let's take a look at the performance payoff, because honestly, these numbers are pretty wild. First off, check out the training overhead. Putting in this whole sophisticated information routing system, it adds less than 4% to the total training time. In the world of large-scale AI, where projects can cost millions and every single percentage point of efficiency matters, that is an incredibly small price to pay. And what about for you, the person actually using the model? How much slower does it get? Well, the increase in inference latency, that's how long it takes to get a response, is less than 2%. That's basically nothing. It means the model gets a whole lot smarter without you ever noticing it got slower. And here it is, the real bottom line. To get the same level of performance as a model with ATNRs, a standard model would need 25% more compute. That is a massive, massive efficiency gain. We're talking huge savings in both time and money when you're operating at scale. But the wins go way beyond just efficiency. The sources show that block ATNRs actually fixed those deep-down technical problems, like the information dilution we talked about, and those unstable gradients that confuse the model. And fixing that stuff, it translated directly into big gains on really hard tests. We're talking 3 to 7.5-point jumps on benchmarks for math, coding, and even graduate-level exams. So where does Attention fit in with all the other modern approaches? Well, you've got stuff like DenseFormer, which uses static weights, but Attention is totally dynamic and content-aware. And then there's MHC, which forces you to completely redesign your model. Attention, it's just a simple drop-in replacement. It gives you this incredibly powerful solution with the least amount of friction. So what's the big picture here? What does all this really mean for the future of AI architecture? Well, it all comes back to that one key idea: active routing. Look, the key takeaway is this. Attention isn't just some small, incremental tweak. It's a fundamental shift in how we think about designing these networks. We're moving away from building passive pipes where information just kind of flows, and we're moving towards creating an active, intelligent nervous system that can route information with real purpose. And that leaves us with this one last, really fascinating question. For years now, we've used the attention mechanism to help models understand language, but ATNS proves we can use that exact same mechanism to help the model understand its own internal structure. So, what if attention becomes the key not just for processing data, but for building smarter, self-optimizing AI architectures from the ground up? Think about that.